about this term. First of all, neutral atoms only. When we're talking about atomic radio, when you're talking about an atom, you're talking neutral. If you weren't talking about a neutral one, you'd be calling it a watt. Instead of an atom, you would be calling it a watt. What's a charged particle? Ion. So we're not talking about the ions, at least until we get to section 5. We're talking about neutral elements. Okay, and so don't confuse this part with that part. Okay, and what's a radius? We think of an atom as being a sphere. And so when we say, what's the atomic radius? You're just talking about from the center out to the edge. And they chose to use that instead of diameter or volume or some other measurement. Here are the facts. And this is the way to learn it. I use an arrow system, and I always do my arrows the same way. That I'm going from left to right, and this means across a period. And then I go from top to bottom, and that means down a family. Now, I've seen folks that do it every which way, like this way and then this way, and it becomes hopelessly confusing. So I always do it the same way. This is what's been found. As you go down any family, the atomic radii was found to increase as we go down a family. As you go across any period, oddly enough, it was found to decrease. And that's probably just the opposite of what you might guess. Those are the facts. Now let's take a look in your chapter. On page 182, if you have your book, you might want to open it to that page. On this page, they are taking some of the representative elements. They've left out the B family. But you see how they have 1A through 7A. They're also including the 8A or the noble gases there. These are the actual measurements. Now let's take that 1A family. We've got hydrogen, and it shows, and absolutely you do not need to know these numbers. I would have to look up here to know the numbers. Hydrogen, its radius is 0.37, but now the units, angstroms. And so let's go back. Back in chapter 1, we talked very, very briefly, and in lab 7 we had one problem. 1 angstrom, which is abbreviated this way, was 1.0 times 10, and let's do it centimeters. Does anybody remember the power on this? Minus 8. Good. So we are talking small. Why do we do that? Why don't they give this in centimeters or meters or something? Because they're incredibly small numbers to have to say and write. So for convenience, we switch to angstroms when we're talking about the size of atoms or molecules later on. And so these numbers, if I look at lithium, what this really means, if it makes more sense to you, 1.52 times 10 to the minus 8 centimeters. So that should impress upon you, we're talking small. So for convenience, they're just saying 1.52, and it's angstroms. So as you go down through this 1A, let's just do this one. We've got lithium at 1.52, and we've got sodium at 1.86. Is that an 8 or a 3?
Looks like an 8.
8, okay. And then potassium, 2.27, and so forth. But the point is, increase. Whether I'm talking about the 1A, or I'm over here with the noble gases. Increase as we go down. Now, perhaps if you have an eagle eye out there, you'll say, oh, but there's an exception here and there. We do not care about the exceptions. But I want you to know the basic trends. And if you answer the questions based on these trends, you will be fine. So we're not going to consider any of the exceptions. If we take a period, like the second period, where you go lithium through neon, and up here it would be lithium through neon. You can see that The overall trend is to decrease. And again, there may be some exceptions there, but we don't care. So first level of understanding, know the facts. Okay, second level, why is this true? And these are the explanations they've come up with because the facts came first. I don't think people, the general public, realize how so often, for chemists or scientists in general, you got the facts first, and then you do everything you can with your brain to come up with an explanation for those facts. Okay? Like gravity. People knew, you know, you drop something, it falls. That's the fact. So what did they come up with as an explanation? Newton got in on this work. You hear the story about an apple dropping on his head. May or may not be true, but he was one of the big thinkers about gravity for the first time in the, I think, 1500s, or 15 to 1600s. 1600s, I think, is when he was born. Okay, this is like you as a teenager, perhaps. Okay, here's the setup. If I told the story again, somebody give me a polite hand gesture that I'm repeating myself. Okay, when you're a teenager, let's say you had a curfew, and your mom said you have to be in by midnight on Saturday night. Okay, so one Saturday night, though, you come dragging in at 2 a.m. That's the fact. Okay, your mother is awake. The woman has a watch on her arm. Okay, so she knows you're dragging in at 2 a.m. So didn't your teenage brain start doing everything it could to come up with an acceptable reason why you're 2 hours late? Okay, so maybe it runs through your brain, I'll tell the woman I had a flat tire. Okay, but before those words even spew out of your mouth, you think, no, she can look in the trunk of my car and see the spare has not been touched. Okay, I better not tell that. I mean, we're not speaking the truth here. We're just thinking of what's an explanation that's going to be acceptable. Okay, so you don't say that. What you do say is say, my friend Karen didn't have a ride home, and so I had to take Karen home. And your mom says, well, that's really weird because I talked with Karen's mother and she got home by midnight. So where have you been? And you say, oh, Mother, did I say Karen? I meant Sharon. I just met this new person at the dance tonight. Her name's Sharon, and you don't know her. She's from that other high school. Okay, that story's going to hold until maybe some more data comes in. Okay, and that's good enough for your mom right now. You're not really going to tell the truth. You've been out drinking with this guy or whatever. So, you're trying to come up with a logical explanation. I don't mean go lie. Okay, but we come up with the best explanations we can. All right, like when I make a mistake on the board and somebody catches me, I'll say, oh, I did that intentionally to see if you were paying attention. When really I was probably daydreaming or something. Okay, so here's the story they came up with, and they're going to stick to it until something else comes along that's better. And this happens all the time in science. As instrumentation gets better, then we can explain things better. Okay, here's what they said. Okay, let's go down a family first, because that's the easier of the two to understand. Okay, what dictates size? Where your outermost electrons are. Because remember, way long time ago, as we started chapter 4, I said, okay, a crude picture of the atom. Here's the nucleus. Then here are the energy levels, and this is where the electrons are found. And we talked about, in the nucleus, all of your positive charge and essentially all of your mass, and almost none of your size. Okay, out here on the energy levels where the electrons live. Okay, almost no mass, but all of the negative charge and all of the size. And that was the day I said, if you took an olive pit or a cherry seed and put it on the 50-yard line in a football stadium, that would represent the nucleus, and the rest of the whole football stadium, all of it, would represent the atom. So your size is coming from where the electrons are, and the size is dictated by the outermost energy level that's occupied. Doesn't have to be full, it just has to be occupied. Okay, with that in mind, Hydrogen. Here's its nucleus. It's got 1 electron. Where is it? What major energy level? First. Okay, if I move to lithium, here's its nucleus. Its outermost level is which major level? 2. Because with lithium, you'd say helium core 2s1. It's out on the second. If I go to sodium, we have a neon core, and then I've got 3s1. So we've gone from the first major level to the second to the third. So hey, why are they bigger as you go down? Electrons are in levels that are further from the nucleus. And so that's a pretty simple, and sounds good, we'll accept it. So electrons are in major energy levels further from the nucleus. Okay? It's a distance thing. 1s, or pardon me, major level 1, 2, 3, 4. Okay, this one's harder. That's what's found. And that's what our picture shows us here. It is decreasing. But if you look up there at the periodic table, let's take the second period again. Well, if I look at atomic number, it goes 3, 4, then 5 through 10. The atomic number is increasing. If you look at the atomic mass, also called atomic weight, it is increasing. Everything you see up there about it increases. And I bet, back when I first heard this story, if I would have put money one way or the other, I would have guessed wrong. I would have thought they're going to increase as we go across, and that isn't what is found. So how do they explain it? Okay, would you buy this idea? If you've had a physics or general science class, you got a positive and you got a negative, and they're attracted to each other. All right? Opposites attract. And you've seen that on OWL as well, if you're doing OWL. Okay, more attraction, more positive or negative charge, more attraction, right? Okay, these electrons out here on the second major level, because in the second period, yes, we may be filling a 2s and then a 2p, but it's still the second major level. And each electron is thought to be acting relatively independently of the others. They're each doing their own thing. Okay, here's a lithium. How much positive charge does lithium have in its nucleus? Now, I'm not asking what ion it forms. I'm saying, how much positive charge does a lithium have in its nucleus? +1. +3. Good. Because, remember from chapter 1 and 2, that 3 means we have 3 protons. That means 3 positive charge, because each proton is +1. Okay, so here's this electron out here on the second, and it's feeling +3. Okay, if I move to beryllium, how much positive charge in its nucleus? 4. It's got 4 protons. Okay, out here in the second, these electrons now each feel +4. Okay, let's move over, say, to nitrogen. Okay, how much positive charge does a nitrogen have in its nucleus? +7. Okay, these guys are attracted now to +7. Okay, here's the basic idea. If you have more attraction, you're going to be sucked in just a little bit. Because he's got +7. Hey, I'm really attracted to that guy. Okay, it's like lithium's got $3 in his pocket. You're going to be very attracted to that guy. I'm equating love and attraction with money, and whether I really think that or not is immaterial. But for the analogy, lithium's got $3 in his pocket. I don't care about getting much closer. But by the time I get to neon, hey, $10 million in this guy's pocket and checking account. Okay, or savings account, even better. Okay, you're going to be really attracted. Wow, $10 million, here I come. Okay, so more attraction, then it's going to suck them in just a little bit. That's why we're getting a little bit smaller. Now, as you can see, going across a period, the effect is not quite as great as going down a family. But that's okay. How they explain it is this. Effective nuclear charge is increasing as you go across, attracts it better, pulls them in. Okay? Yeah. It's hard to put that in a nice, concise sentence, but effective nuclear charge is increasing and therefore attracts electrons better and pulls them in closer. So every trend we see today, we're going to look at three. Maybe we'll get them all three done today, maybe we won't. But what are the reasons? This level 2 that we're talking about, first it's the facts and second are the reasons. Here it's a distance thing. Major level 1, 2, 3, 4, end of story. This is more subtle. Why is it decreasing as we go across? Is because they're getting attracted more. Effective nuclear charge. Now, Bruce, did you have a question?
I was trying to put it in my brain another way. Could you consider them to be more dense as they go? Is that why the noble gases are so stable?
Actually, the usual response about their stability is because they have a fine electron configuration. Every sub-level is full, every major level is full, and evidently that confers a lot of stability. What do you find? This is not a good analogy at all, but for a dog to be stable, physically stable, no, they're never mentally stable. Okay, for a dog to be stable, it needs 4 legs, right? So if it has 4 legs, it's happy. It's not going to go try to grow another leg or get a prosthesis. Okay, but if your dog has 3 legs, now he can live, but he's not real stable. He's got to work on, I've seen 3-legged dogs run, so they can do it, but they're not as stable on their feet. If they got in a fight, it'd be easier to knock them out. And so the electron configuration, evidently, if you've got a full level, that confers a lot of stability. So those are the 4-legged dogs.